In this video, I'd like to take a look at the concept of sample variability and what standard error is and how it's used to help us to infer what the population mean is from a sample mean. The specific learning objectives are going to be when to use standard error or when standard error is calculated, um, the standard error formula used for that calculation, the variables that are associated with standard error and what they mean and how they help determine sample means variability. And then introduce how standard error is used to build buffers around the sample mean as a way to estimate what the range of values for your population mean are. Kind of an introduction to the concept of confidence intervals. But we'll do a separate video on creating confidence intervals. So in the world of process improvement, frequently we're going out and capturing data on either current or future state performance. And the problem is that frequently the population data, um, it's not known. It either hasn't been captured or we don't have an understanding of it. So instead, we like to capture a sample. And we'll go out and do direct observation or pull a small piece of historical data. And the idea is that the sample should be a reflection of what the overall population is. Frequently, when we're working with sample data, we perform descriptive statistics on it and we capture an average, and we know that the mean for a sample is represented as X bar. And what we're hoping to do is we're hoping that that sample mean is a reflection of what the population mean or mu is. Samples are captured to help infer what the population means true value is when we don't know what the population's true value is. So in a nutshell, if you've got population data to work with, you're probably not going to work with samples and you're not going to need to worry about sample variability or standard error. But when you are working with samples and you're using sample means to be a reflection of population means, we're going to need to take a look at the variability that might be inside this sample. Not all samples are always the same. Because some of your samples can vary from one sample to the next, we need to deal with this fact that not all samples are the same, and that's when and that's what takes us to sample variability and standard error, a tool to help us to understand and measure that variability in samples. When we're dealing with samples to understand populations, then we need to take a look at sample variability and standard error. When it comes to measuring sample variability, I like to use a little analogy to kind of help frame what the eventual formula is that we'll be taking a look at. And let me just give you a little snapshot of what the formula is, and then give you the analogy, and then we'll come back and explain the formula in detail. So eventually, this little story about soup pots and ladles is eventually going to get us to the standard error formula, sigma over the square root of n. And we'll come back to this formula and see how it's used to help us to better estimate population means in a moment. But let me get this out of the way and tell you a little story about making soup. So when I was a little kid, I remember going to my grandma and grandpa's house and watching my grandma make big pots of soup. And in this story, the big pot of soup is going to be an analogy for the population data you have for a process improvement project. It's all of the data. It's all of the soup. And it was a big old pot. I mean, I don't know how many gallons, but I couldn't put my little arms all the way around this pot. Big pot of soup for her making chicken noodle soup. And as she threw in all of the ingredients and mixed it all up and let it cook for a period of time, eventually she wanted to get an understanding of what is the current state of the big pot of soup. And so she didn't have the means to be able to eat or drink all of that soup. I mean, that would defeat the purpose. She instead would grab a small sample. And I remember my grandpa coming up to the big pot of soup and grabbing it with a very small spoon, like a soup spoon, and he'd dip it He'd dip it into that big pot, grab a very small little soup spoon, and slurp onto it and say whether he thought it was tasty or too salty or not enough chicken, not enough noodles. And my grandma would always say, no, 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 no. You need to have a little bit bigger ladle if you want to have a true understanding of what this pot of soup is. The first thing that she would do is she would take that big ladle and mix it up in the pot, in essence, creating a random sample. And then with her bigger ladle, she'd then scoop that up and take a look at the makeup of chicken and noodles and carrots versus everything else and take a small slurp from that and make a determination about what the underlying population of soup was. The smaller the sample size, the smaller, in this case, the spoon that was being used, the less certain she was that she had a real representation of what was going on in the big population of soup. So, in some ways, the size of the sample uh, plays a role in the variability of whether or not that sample is a reflection of what the true population average is. The bigger the sample, the smaller your sample variability will be. So size of the sample matters. But there's another thing that was happening in the soup analogy, and let me just clear up the screen a little bit. All right, back to the soup analogy with the pot. Inside the pot, there was a lot of different ingredients associated with my grandma's chicken noodle soup. I mean, you had the actual chicken, but you had the carrots, you had broth, noodles, spice, celery, parsley. There was a bunch of stuff that was inside my grandma's chicken noodle soup. And so when she mixed that thing up and grabbed a ladle full, she wanted to make sure that the ladle had all of the elements that were associated with the population of soup. What if what she was making was just simple broth? If it was just simple broth, there wouldn't be quite as important a need to have a big ladle to capture all of the different pieces that are inside that population of soup. You know, if it was just broth, my grandpa's technique of using just a little simple soup spoon, it probably worked because you didn't have to worry about whether you captured all the noodles and carrots and everything else. The variability of the underlying population's data set plays a role in how big a sample you need. If you've got a population with all different types of values, and now I'm going to go back from the soup to actual process performance data. If you've got a process in which performance is all over the board, you're probably going to need a little bit bigger sample than if your process performance data is super consistent. Like, let's say that we had a big old pot of data, and every data point was the value 100. The piece of lumber that was being cut was 100 inches long. The time it took to complete the transaction was 100 minutes or 100 seconds. So you had all of these data points in the pot. Each data point that is in red represents 100 for its value. To do the average for that data set, well, that's easy. If every single data point is 100, the average is 100. If I were to grab a small soup spoon and grab a couple of these red data points, the average would be 100. If I were to use a large soup spoon and grab data points, the average would be 100. When there's no variability in the underlying population's data, the size of your sample can be smaller. You know, if this was not, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points in here, if this was 10 million and they were all the same, I wouldn't need a very large sample to get an understanding of what the entire population's average was. And if there was very tiny amount of variability, and let me show a little bit of variability with a different data ball. So let's say that the blue ball represents not a data point that's 100, but a 100 and let's call it 90. The average here is still pretty darn close to 100, and if I did a small scoop and I grabbed a small sample over here, or a small sample over here, and its average was 100, my overall population average would be a little bit different than 100, but pretty darn close. Even if I did grab a small sample and it included that blue data point, the size of my sample average as compared to the population average would be pretty small. If you have very little population variability, then the size of your sample does not need to be as large. But if this bowl of data points was all over the board, we had blue and green and yellow and red and purple and black, and they all represented different data point values, we need a little bit bigger spoon to grab a sample so that that sample reflected what the true population average was. The way that we measure the variability of the data inside your population, well, we've covered that in earlier videos. To measure population variability, it's a simple calculation. It's the standard deviation. And so we could, if we had the known population data laying around, we could highlight that data in Excel, press the standard deviation button, and represent it as sigma. Sigma is a measure of the variability in your population. So to boil it down, when we're looking at samples, we need to consider the size of the sample, but we also need to consider the variability of the population, or sigma. And so now let me clear up the screen and bring back a formula that I showed you just earlier before the story started. So if your sample mean is going to be used to reflect the population mean, and remember sample mean, the way that we represent that, x bar, or we could write it out as x bar. But if x bar is to reflect your population mean, which we know for population mean, that's reflected as mu, there's a couple of things that we need to consider. We need to consider the size of the sample, and the size of the sample is going to be reflected by the term n, number of data points. But we also need to consider the variability of the underlying population. If we have data points all over the board for our underlying population, we're probably going to need a bigger sample to better reflect what's going on. And if the underlying data population has very little variability, all the data points are almost the same, it's not going to matter as much. So if we want x bar, our sample average, to in some way reflect what the population average is, we're going to have to consider the size of the sample, n, but also the variability of the underlying population, sigma. The way that we incorporate all of these variables into a better understanding of how the sample mean can reflect the population mean is to use a term called standard error. Standard error is the built-in error that all samples have when the sample mean is being used to represent the population mean. And it has to incorporate the size of the sample and the population variability. And the way that we determine standard error, it's equal to that standard error then, as your sample sizes get larger, standard error gets smaller. As the population variability gets smaller, or there's much more consistency in the population data set, that standard error gets smaller. And how we use standard error is we'll build on the high side and the low side of our sample mean calculation, which we call x bar. We'll build on the high side a standard error, and on the low side, a standard error. These range of values where we take x bar and we add standard error plus a fudge factor, and then we subtract standard error plus a fudge factor, this range of values is where the population mean will be located. Mu will be somewhere between these range of values. Standard error is used to help build a buffer around your sample mean to help describe what the true population mean value is, because all samples vary. Each time you grab a sample, there's a chance that each sample is going to be a little bit different from this underlying population. So we build in standard error. Standard error calculations, very simple. And then we use that standard error both on the high and the low side of X bar to come up with an estimate for what the population mean is. And in our next video, we'll take a look at building that range of values, something we call a confidence interval.